I'm Lytle, like Lily just mentioned, and my topic today is toward optimization for the CO2 and electricity grid. So just to start off, I'm going to give you an introduction to my topic, give you some background, then I'll talk about the data that I'm using, and then I'll get into the optimization and the initial results I have and the current and future work that I will be working on. So just to start off, my project, we are focusing on Southeast Asia, just because, as you can see here, the energy demand has been rapidly increasing or steadily increasing through the last so long, and this is the last 20 years visualized here, but we have been focusing on this region just because, like we heard before, some of it is more underdeveloped, and we need to think about ways we could optimize these systems. So along with the energy demand, we have the energy production within the region. And as you could see here, it is split up, but it varies depending on what country you're looking at. But if you look over here, the coal is about half of the energy production within year 2022. And so for my project, I've been focusing on the coal-fired power plants within the region, just because they do produce a lot of the energy within the region, but as well, they are one of the highest producers of carbon dioxide within Southeast Asia as well. And going to that, as you can see here, these are the breakdowns of carbon dioxide annual emissions within the region. And so as you can see here, there is a lot of carbon dioxide that's being produced, and we want to find a way to optimize it and mitigate those emissions. So getting into my project, I just wanted to give you a basis of the network that we are looking at to optimize. So this is a basic carbon capture and storage network, and I'll go through it quickly just for the people that might not know. So like I mentioned, I'm working with coal plants, but you take different forms of fuel and you put it into the power plant, which in turn produces electricity and in turn also produces carbon dioxide, which, as we know, is bad for our environment. So that's why processes like carbon sequestration come into place. So we capture the carbon from the gases out of the power plant using temperature and chemicals and get the pure carbon dioxide, which then is transported through shipping, pipeline, and liquid or supercritical state. And it could be also in truck, but shipping and pipeline are the most common. And then stored onshore, offshore in geological formation. And yeah, so this is the basic problem we're looking at to optimize. So getting into the data, I looked from Alita's paper in 2022. We have the oil and gas reservoir data for the region, which are common to use for carbon sequestration, and we have good data on it. So I'm focusing just on the oil and gas, depleted oil and gas reservoirs to look to optimize. And so all these green dots here are different reservoirs. And as you can see on the right here, the different the size, the larger the capacity of them. And this is an example of Tunu, which is that big, larger circle right over there. And we have the capacity data as well as injection and costs. And so these are the top 8 oil and gas reservoirs, like the largest capacity within the region. So I'm starting to look at these 8. And on the other side of the carbon problem, we have the sources, which are the coal-fired power plants, like I mentioned before, which I got from the Global Energy Monitor data set. And the same thing, the larger the circle, the larger the annual emissions. So this one you see right here, this is the largest emitter of carbon dioxide within this region, which is that circle right there. And so these are the top 10 largest carbon dioxide emitters within the region as well. So I am focusing on those to formulate the optimization. So getting into the optimization, the main goals we're looking at obviously is to mitigate carbon emissions, but then also to minimize the costs. And so there are three main costs that we want to minimize within the carbon source to sink situation. And the first is minimizing the capture cost. So at all these 10 power plants, they have a little varied capture cost, but within Southeast Asia, it's a pretty average capture cost. It will depend where you are in the world. It could vary, but it's about $50 per ton of carbon dioxide. And so that is the first cost we're looking at. The second cost is the transportation cost. So we're looking at getting the cost from point A to point B, like I mentioned before. You could do it through ship, through pipeline. And to make my optimization a little more simple, I'm looking at the just average pipeline costs to formulate the optimization. And the third cost that we're looking at is at the sink, which is the injection cost. So through these fields, we have the basic injection costs, but they do depend which oil and gas reservoir you're using, if you're using different types of aquifers as well. But so this is just the three main points we're looking to optimize. So getting into the optimization problem, I set up initial constraints just to make it feasible. And the first constraint is the emission constraint. We basically want to get all of the carbon that is produced annually from each power plant into a reservoir stored underneath the ground. So for example, this power plant here produces 4.5 megatons of carbon dioxide. You want to make sure that within the parameters, it will all get stored within the year. So everything that's being produced every year will be getting sequestered into the ground. And so the second constraint is the sink capacity constraints. So as you see here, we have 3 power plants and 2 of the reservoirs. So at each of the reservoirs, they have a max amount of carbon dioxide that you could store in the ground. And so within the time parameter of the problem, you want to make sure that you don't exceed that capacity, as well as there is an injection rate, which you can only inject so much carbon dioxide into each reservoir per year. So you do not want to exceed that rate as well. So for example, as you see here, there's 2 plants, and the Taoyuan Power Station, it might be easier to send it and more cost effective to send it to the Subian reservoir, but the injection rate is a lot smaller, so you could only send so much to there per year. So you have to as well send some to the Arun reservoir, just to make sure, like I mentioned before, you get all the carbon that's produced per year into the ground. So within the capacities, you just want to make sure you don't exceed the reservoir capacity as well as the injection rate amount. And then, of course, the last flow constraint is the flow constraint. You want to get all the carbon from point A to point B. It can't go from point B to point A. We can't have a negative flow in these systems. So using all of these constraints, I formulated the optimization using the CBX program, and I got my initial results. So just to explain what you're looking at here, all these lines are connecting these 10 power plants to the 8 oil and gas fields, figuring out where is the most optimal way to send the carbon dioxide to minimize the costs and emissions. So looking here, like I mentioned before, we have this power plant here, which of course it needs to be able to send all its carbon out. Because these power plants here are already sending their carbon, and that's the most optimal cost-effective way to send it there. It's filling up the injection capacity for that year. So power plant number 7 could only send so much to one of the reservoirs, and it has to send it to the others, as well as just the amount of carbon dioxide is split evenly to minimize the costs. But overall, this is the initial results, and just to go to the conclusions, the preliminary results show some significant potential to reduce emissions and costs within the region. But of course, we have to understand the assumptions of political and economic factors that we cannot control all of those. And of course, that will go more into the future results to see what policies we could add in, as well as different economic factors with who's willing to share what as well. So looking into the future, like I mentioned before, we're looking at the electricity grid. So what you're looking at here, these blue lines are the current transmission lines within the Southeast Asian region. So they are the main ways to transport power around these countries. And so, of course, as we know, you need power to run almost everything these days. So it's really important to understand that we want to also optimize those costs. So there's a generation costs that go along with it, but what you're looking at here is just to visualize what we're looking at. All these green dots here are the top producing coal power plants per each country. Just to visualize what we're looking at here and showing that there are some countries that might not get the power demand that is necessary to run it, or they're just relying on the base power needs, like the Philippines, for example. They don't have as much access to sharing energy, so they do have to rely on the base power, as well as some other countries are more developed and have more access to that. And that's another problem we will look at for the future. But the second future work that I'm currently working on is we want to connect the electricity grid and the carbon grid network. So at these buses, which are just the junction of power, which, for example, is the coal-fired power plant that I was looking at currently. It could also be renewable energy, other forms of power for the future as well. But we have the load, which is the power demand, and then the generation, which is the power produced. And it's connected to the carbon grid at the generation, because obviously as you're generating electricity, you generate carbon dioxide. So this is just a basic example of what I am planning on connecting to the future once we finish the electricity optimization. But yeah, I think that's it from me. Thank you.
Questions for Lytle?
Yeah, that is pretty interesting. I'm just trying to understand that software. Is it assuming a constant cost for transmission or transportation, just simply dependent on distance, or get other factors?
Yeah, so right now I'm using average cost using the pipeline as a base, but for the future, I want to work on getting specific costs for shipping and pipeline added in there. But obviously, it will be less expensive to put the infrastructure for pipeline over shorter distances, and shipping will be more cost effective over longer distances, and that is something I am considering for the future. Yeah.
Excellent, thank you.
Yeah, Wayne?
Yeah, so I appreciate your consideration for like constraining your models with, you know, as you said, political and economic factors which are out of your control. But I was curious to know, like in your mind, what are like the political or economic status quos, or like even technologies that could make like the biggest difference